Okay, so now we are going to go ahead and get started into our key reactions that we're going to hit for chapter 17. So there are a lot of reactions in chapter 17. However, for the electrophilic aromatic substitution reactions, we're going to just focus on 4. And so our focus is going to be on the chemistry of nitration, the chemistry of bromination, the chemistry of alkylation, and the chemistry of acylation. So we are just going to study these first 4 reactions. Where we're going to begin right now is with nitration. So if we are doing nitration chemistry, so of course we have a benzene ring. Okay, so we are going to have benzene. And remind me, what is the best kind of group that needs to be bonded to benzene to do this electrophilic chemistry? And so for the groups, should I have electron donating groups bonded, or should I have electron withdrawing groups bonded? So what is going to be the best kind of chemistry? I'm going to let you think again for just a moment. If I'm doing our EAS chemistry with a benzene ring, what kind of group should be bonded for the best chemistry? Electron donating or electron withdrawing? Keeping in mind that we are going to have a pi bond attacking some good electrophile. And the answer is, and you are all correct, I need to have an electron donating group. Okay, so for nitration chemistry, the best chemistry, benzene, an electron donating group, and I am going to add to that some nitric acid. And I am going to add to that some sulfuric acid, H2SO4. Okay, so let's look at the chemistry. So what has to happen first is first for nitration, we have to first create our good electrophile. So we have to create these things. We can't just buy these incredibly strong electrophiles. We actually have to make them. For nitration, we have 2 steps. So let's go through the words and then we will draw it out. So in the first step, we are going to mix sulfuric acid and nitric acid, and we're going to get a nitronium. And then after that, our benzene will react following the general mechanism that we have learned. Okay, so let's talk about the sulfuric acid with nitric acid. What happens in the first step is that the nitric acid gains a proton from sulfuric. The second arrow is going to be, I break that bond, put those extra electrons onto the oxygen. The result is I have protonated nitric acid, and then I have formed the conjugate base of sulfuric, the HSO4 minus. What happens next is that this protonated nitric acid group, then in one step, lone pairs from the oxygen come in to form a new pi bond. I lose that water as a good leaving group, and I get a nitronium ion as my very good electrophile. So this nitronium is an excellent electrophile that will then do benzene chemistry. Okay, let's draw that out. So let's say that we are doing nitric acid. So we're doing nitration with, let's do phenol. So to remind you, a phenol, I have a benzene ring and I have an OH. So let's say I'm mixing together phenol. I'm mixing together sulfuric acid, so H2SO4, with nitric acid, HNO3. Okay, so what is that first step of the chemistry? So the first step of the chemistry, the oxygen from the nitric acid abstracts the proton, electrons move on to the oxygen, and I get my protonated nitric acid, and then I would have minus HSO4 as a byproduct. Okay, that's the first step. Then what happens? The lone pair from the negative oxygen moves in. I kick off water as my good leaving group. And so then that gives me a nitronium ion as my excellent electrophile. Now I do chemistry with phenol. Okay, OH. An OH group is an activating group, and it is an ortho para-directing group. And I'm going to choose, let's say, I'm going to do para-chemistry this time. Okay, so for para-chemistry, I'm going to take this pi bond. It's going to attack the nitrogen. That puts too many bonds around nitrogen. I need to kick off the oxygen as a good leaving, or just kick it out onto the oxygen as an extra lone pair. So now what do I have? I have the phenol. I've done no chemistry there, no chemistry there. I've added my new electrophile to the para position. So now it looks like this. My neighboring carbon becomes the carbocation. And then I can draw in with that 1, 3, 5 relationship all of the positions of the positive charges in the resonance form. Again, here notice that this particular carbocation is especially good. It is like tertiary-like. I have my positive charge directly below my electron donating group to make a really good cation intermediate. Okay, what happens in the next step? In the next step, we have talked about we have some base that is going to remove a proton from the same carbon as our new electrophile. And what we have in solution is that minus HSO4. It is going to remove the proton. Electrons go in to form the double bond. And our final product, H, we have the nitro. And my final product is going to be para-nitrophenol. Okay, and so then that is nitration chemistry. So first I have to form the nitronium electrophile, and then I do that benzene chemistry. So now let's look at a second kind of chemical reaction. Let's look at bromination. So the steps are the same. First, I need to form my very good electrophile. Second, I react with benzene. Okay, so how do we get our good electrophile for bromination? Here is how it works. So I would take bromine Br2, so I would take Br2, and I add to it FeBr3. FeBr3 is known as a Lewis acid. A Lewis acid will accept electrons. So the bromine will actually add to the iron, add to the FeBr3, and then I get this really unique complex. So this complex is simply called like FeBr5. I get this really unique FeBr5 complex. So in this complex, how I like to draw it out is I have a positive bromine at the tail end that is strongly interacting with a minus FeBr4 piece. So this bond between that very last bromine and this FeBr4 piece is in between a covalent and an ionic bond, and I like to write it out as an ionic bond. That really highlights that that bromine has a positive charge and is therefore very electrophilic. Okay, so our benzene chemistry, one of the pi bonds attacks at the electrophilic bromine, I would completely break apart this FeBr4 piece. The result is that I get a carbocation and then the minus FeBr4. So what happens in the next step? FeBr4 acts as that base that takes the proton from the same carbon as my new electrophile. They move in to form the pi bond, and I get my brominated product as the final product. So those are the two steps. Okay, so once again, let's go ahead and do one more practice problem. So let's say that we were brominating. Let me think of something that comes off the top of my head. Let's say that we were brominating. Oh, I know. Let's just go ahead with nitrobenzene. Okay, we're brominating nitrobenzene. So I have my nitrobenzene and I'm adding to it Br2. And then I'm going to add to it that Lewis catalyst FeBr3. Okay, so what's going to happen first? I am going to have the bromine add to my FeBr3. And that gives me this really unique complex where I have bromine strongly interacting with an FeBr4 minus piece. Okay, and then here is my very good electrophile. Okay, so I made my electrophile in step 1. So now in step 2, I'm going to do my chemistry with the benzene ring. Okay, let's think about that nitro group. So what kind of group is nitro? So here are your questions. Is the nitro group an electron donating group, or is nitro electron withdrawing group? Okay, think about this for a couple seconds. Nitro, electron donating or electron withdrawing? And the answer is, yes, you are right. It's electron withdrawing. Okay, let's go into our next practice problem. So since I have an electron withdrawing group, am I activated for chemistry or am I deactivated for the electrophilic aromatic substitution chemistry? So which is it? Am I activated or deactivated? So think about your answer for a couple seconds. Is the chemistry activated or deactivated? You are correct. It is deactivated. Okay, next question. Then for this electrophilic aromatic substitution that is deactivated with a nitro group, is the new group going to be added ortho, para, or is the new group going to be added meta? And so what is your answer? So I'm deactivated, I have a nitro group, ortho, para, or is it meta? And does everyone have their answer? Great. You're right again. It is meta-directing. So now let's go ahead and draw that meta-chemistry. So I have my good electrophile. I take this distant pi bond. I add to the bromine. I get my sigma complex intermediate. My new bromine is in the meta position. My cation is in the para position. I can go ahead and draw in all of the 3 resonance forms and recognize again, I never have the cation beneath the electron withdrawing group. So that's great. My cation never beneath my electron withdrawing group in any of the resonance forms. So now what is the last step of the chemistry? The minus FeBr4 is going to act as a base. is going to take the proton from the carbon with the new electrophile. The electrons move in to reform the pi bond. And I have my new product, my nitro with my meta-bromo. Okay, let's just do one other fun chemistry before we tie up this short video on the first two reactions. So I want to do just this. This is one that came to my mind as like a fun practice problem for us to do. So let's say that we have just conducted bromination. So we did benzene. And with benzene, we added Br2 and we added FeBr3, and that gave us bromobenzene. Okay, that bromine could be at any carbon. I've just randomly chose the top carbon. And now we want to do some other chemistry. And so actually, let's just do chlorination chemistry. So chlorination is Cl2 and AlCl3. So what is going to be that final product? Okay, let's go through the steps. So first, we need to make our very good electrophile. So the chemistry is exactly like we just learned for bromination. The chlorine is going to add to AlCl3, and that creates this unique complex where I have a positive chlorine that is really strongly associated with a negative AlCl4 piece. Then I am going to have my bromobenzene react with my chlorine electrophile. Okay, so let's go through the same kind of discussion we did earlier for electrophilic aromatic substitution. Is the bromine activated for chemistry, or is it deactivated towards chemistry? So which is it? Yes, it is deactivated for chemistry. And that's because bromine is an electron withdrawing group. Okay, next question then, is it going to be ortho para-directing, or is it going to be meta-directing? And the answer here is, you have your answer, and it is ortho-para-directing. Remember, halogens are kind of those weird ones. So the halogens are deactivating, but they have lone pairs. And because they have lone pairs, they are very good at stabilizing cations. So therefore, they are ortho-para-directors. So let's do this chemistry. I'm just going to go ahead and randomly choose orthochemistry. So I'm going to take this pi bond, the near pi bond, attack the chlorine. I have that. My neighboring is now the cation. Notice now my cation directly beneath the bromine with its 3 electron donating groups that can help stabilize that cation. And then the next step, it's going to be the minus AlCl4. So it's going to be this minus AlCl4 that comes in, removes the proton from the carbon with the electrophile. Those electrons go in, and then we would have a benzene ring that has both bromine and it has both chlorine attached. Okay, so what do you think? If I were to send you into the lab and do this chemistry, do you think you'd get 100% yield? Would it be 75%? Would it be 50%? Would it be 25%? What is your gut instinct? How much product am I going to get? Well, if I were predicting off the top of my head, I'm going to go 25 to 50% at most. And that again comes down to the fact that I am doing chemistry with a deactivated bromobenzene complex. So I'm going to guess less than 50% yield. What do? I would head up into lab and I would run the chemical reaction. Okay, so this ends the video. We have studied nitration chemistry, bromination chemistry, and actually I threw in chlorination because that is a very easy reaction to study because it is much like bromination. Okay, see you in the next video where we will discuss alkylation and acylation.